In this class we are going to introduce the liquid extraction, and I will take one more class on the liquid extraction. On top of that, later on I will also talk about two-phase aqueous extraction, reverse micellar extraction, because extraction is one of the most important downstream steps. So, we need to spend more time on that, especially for biomolecules like proteins, carbohydrates. We cannot use distillation or any other harsh approaches. So, liquid extraction is the best way of doing things here, because you are doing it at mild conditions, almost at buffer pH, and the temperature will be at room temperature. Okay. So, what does liquid extraction indicate? It is a mass transfer operation. A liquid, there are two liquids, we have a solute in one liquid, okay, and that gets moved or transferred into the solvent phase, and both these phases have to be immiscible. That is very important. The solute in the heavy phase, it is called, or sometimes it is called feed phase, and the solvent is into which the solute gets moved. Okay. So, this is a mass transfer operation. So, we have the feed, we have the solvent can be heavy solvent with respect to feed, or it can be a light solvent with respect to the feed, and then once the extraction is done in a stage, the feed is known, then becomes called raffinate, and this is called extract. So, hopefully the extract will contain more solute than it contained in the beginning. So, sometimes we introduce very fresh solvents, sometimes we introduce used up solvent, and there is an equilibrium which takes place between the feed and the solvent, and the solute gets partitioned. That is the term we have to use, it gets partitioned into the extract phase. Okay. And then later on we can remove the solvent by simple distillation, thereby you get your solute. So, it is, as I said, this is a very important downstream operation which is practiced for extracting metabolites, small molecules, even proteins. Like I said, we have this aqueous, two-phase aqueous extractions and reverse micellar extractions, where even proteins or biomolecules, enzymes could be extracted. So, the solvents that are generally used are like ethyl acetate, chloroform, methanol, and so on actually. Okay. And this is called a stage extraction, one stage. So, you can have second stage, third stage, fourth stage, and so on, so that you could extract as much as the solute that is possible using solvent. As I said, the solvent could be fresh or it could be used solvent, that means it may contain some solute into it actually. So, this is called an equilibrium operation, and this is called a mass transfer operation. So, we need to remember that. So, we can use this for recovering antibiotics, organic acids, lipophilic products, low molecular weight lipophilic products, and if you are interested in proteins, enzymes, antibodies, biomolecules, then we have to resort to two-phase extraction or reverse micelle extraction. So, in two-phase and reverse micelle, generally you have water as the extracting medium, and as you know, proteins and enzymes are more stable in water or the buffer. So, we do not resort to solvent extraction. Solvent extraction is generally for molecules, large molecules, small molecules, metabolites, and so on actually. So, what are the advantages? We can selectively extract from a fermentation broth. So, after we do a filtration or solid liquid separation, the concentration of your metabolite may be very low. So, we need to build up it to maybe 40% or 50%. Okay. So, it is called recovery, and extraction is the normal procedure, and it is very cheap to do. It is generally ambient condition, so stability is not an issue. It is suitable for a wide range of scales. Even in your lab you can do an extraction, and even in large scale, when we talk about thousands of liters of manufacturing scale, we can have extraction. So, that way it is suitable for a very large scale of operation, starting from milliliter or cc, going right up to tons of material that can be extracted using a solvent. So, you can have one stage, you can have n stages, that is multiple stages of operation. Okay. You can have cross flow type of extraction, you can have a counter current type of extraction, and we will talk about each one of them little bit. Okay. So, the problems associated with solvent extraction, sometimes you may have many dissolved solid substances. So, you will not be able to get a good phase separation, there will be complexity of the phases. So, the extraction of the desired product becomes difficult. There could be some surface active agents like surfactants that may be present in your fermentation broth. So, the mass transfer becomes a problem, because there could be a small layer between these two heavy layer as well as the solvent layer, which may be preventing the transport. Okay. There could be particulate matter which may be preventing the separation, phase separation effectively. There could be chemical instabilities because the desired product may be unstable because of some microbial activity or metabolic, that means some metabolites are present which may be degrading your product. Composition or pH conditions during extraction, that may affect the overall efficiency. Rheological property, the viscosity, because fermentation broths are highly viscous, and when you are using a solvent and trying to extract, it is going to be a big problem, because viscosity will definitely affect the mass transfer as well as the extraction efficiency. So, what are the parameters that affect extraction? Solvent, what type of solvent I use, operating conditions, what are the operating conditions, what should be the pH, what should be the temperature, and so on. Mode of operation, am I going to use a batch mode, am I going to use a multiple stage continuous mode, and so on. What are the extractor type? I am going to show you pictures of different types of extractor, and you will be surprised, a large number of extractors are available. Then design criteria, what should be the size of the extractor, should it have mechanical agitation, non-mechanical agitation, should it be a tower type, and so on. Those are all design criteria. So, large type of design parameters that needs to be considered when you have to design an extractor and select an extractor. Okay. So, what is the principle by which extraction takes place? The solute present in one phase gets partitioned or distributed into another phase. This partitioning of the solute is based on thermodynamics, based on partition coefficient or distribution coefficient. So, we call it a partition coefficient. Generally, partition coefficients we assume it to be constant at a given temperature. Okay. So, the partition coefficient should be favorable towards the solvent, the solute so that move into the solvent phase. So, we define K, the partition coefficient, that is the ratio of the solute in the solvent phase, that is organic phase, or it is called extract phase, divided by the concentration in the aqueous phase, or it is called heavy phase or raffinate phase, and so on. So, we can give different names for that. So, this is a solvent phase, this is a extract phase, and this is a heavy phase or aqueous phase or a raffinate phase. So, this concentration is defined as K, and generally K should be very large. Larger the K, better is the separation efficiency. I do not require too many extraction operations. Okay. If smaller the K, then I need to resort to many extraction steps. Okay. So, I need to select the solvent so that the K value is pretty high for that solute. So, for that particular solute, K value should be high, otherwise I need to change the solvent. It is constant at a given temperature. So, we can assume that it does not vary much between one stage to another, as long the stages are operated at the same temperature. So, higher the partition coefficient, greater will be the extraction efficiency. Okay. So, obviously, when I have a higher partition coefficient, greater will be extraction efficiency. I will not require too many stages for separation. Large density difference, better is the extractant and affinate separation, right. If the densities are very high, the phase separation is very fast and very effective. So, if the densities are very difference is very small, phase separation is not very efficient, then I need to wait for a very long time and I will not be able to really see the phase separation. Okay. So, the density plays a very important role, not in the first part of the extraction, but on the settling part of it. High viscosity, this affects the phase separation. If the solvent viscosity is very high, it is not going to immediately separate. They should have negligible miscibility, that means the solvent and the heavy or the raffinate should not be miscible. If it is going to be miscible, you are going to lose solvent. Okay. The solvent should be easily recovered and purified, because I cannot throw the solvent. After the extraction, I will remove the solvent and get the solute, then that solvent should be recyclable. That means I should take it back and put it into my extraction process. It should be easily available, it should be cost effective. So, these are very important. Cost ultimately plays a very important role. Low interfacial tension between the phases, then dispersion of phases is good, mass transfer is good, but then interfacial tension is low, then the phase separation becomes difficult. So, it takes much longer time for the phases to separate. So, if the interfacial tension is low, you get good separation, you get good mass transfer, but later on the settling of the heavy with the light becomes a time consuming process. Okay. And then other physicochemical properties such as boiling point, density, interfacial tension, viscosity, how corrosive it is it flammable, is it toxic, is it safe to handle, all those factors are also considered when you decide on a solvent. Should I take a chloroform, should I take a acetone, should I take a methanol, should I take a toluene, should I take a hexane. So, you decide based on all these parameters, okay, and the type of solute which you are trying to use. So, selecting solvent, we have many criteria, like for example, free base is more soluble in non-polar organic solvents, okay, free base than in polar organic solvent, okay, such as water or aqueous base. If you take quaternary ammonium salts or amines formed by reactions between with acids, they are more soluble in polar or aqueous media than non-polar. So, I would select a polar solvent if I am trying to extract quaternary ammonium salts. If I am trying to extract free bases, then I would rather go for a non-polar organic solvent. If the aqueous solvent is basic, amine compounds may be in the free base form. Okay. Free acid may be more soluble in an organic solvent than in water or acid, okay, free acid. Salts formed by the reaction with base are more soluble in aqueous media than in organic solvent. So, if I have salts that are formed with the reacting with some base, okay, then I would rather use a aqueous media than organic solvents. Acidic aqueous medium will be in the free acid form and so will partition into organic phases. N-butanol, ethyl acetate, MABK, toluene and hexane can be used to extract acetic acid from water. So, N-butanol will have the highest and hexane will have the lowest extraction ability, okay, and N-butanol having the highest and N-hexane having the lowest miscibility with water. So, if I have acetic acid with water, so I would rather select N-butanol because it will have the lowest miscibility with the water, okay, and it will have the highest extraction efficiency. So, there are certain conditions, whether it is a free base, whether it is acidic, whether it is a salt, whether it is a polar compound, whether it is a non-polar compound. So, we can select solvents based on these conditions as well. So, that separation is efficient, miscibility between the raffinate and the solvent is also minimum. Okay. So, what are the equipments that are used? Two types of equipment that are generally used is mechanical agitation, because that will facilitate mixing, and those counter current flow of two liquids, and the main goal is to bring in an intimate contact between the two liquid and allow a high rate of mass transfer. So, here we want to bring a very good contact, we want to increase the surface area continuously between these two liquids, number 1. Number 2, we want to enhance the mass transfer coefficient. So, this is how it is done. So, if you use a mechanical agitation, you get a very good agitation, surface renewal, you are using more energy, but then in counter current systems we have a better mixing also by using tower type of extracting equipments and so on. So, we will look at some of those designs here. Okay, this is the simplest of the lot, it is called a mixer settler batch extractor. So, what you do is you take your feed here and then you take your solvent, you agitate, okay, for intimate mixing, and then you drop it into your settler. So, they form 2 layers, you give sufficient time so that they form 2 layers, and then you remove your solvent and you remove your raffinate. If the solvent is heavy, it will be collected at the bottom, your raffinate will be collected at the top, if vice versa it will be. So, if the solvent is light. So, this is called one stage mixed settler operation. So, I can have many stages like this, okay. Or I can do the same thing, I draw both of them down and then again I can put in my raffinate, I can add some solvent and I can achieve some separation. So, this operation can be done many times using the same setup. So, when every time I do, I will call it one stage operation. So, mixer settler is quite simple, it is a agitator and a settling tank here actually. It occupies a lot of floor space, remember that, okay. Another type is the column extractor, these occupy less space. So, tall columns are there, okay. You can see the tall columns here, you have a solvent coming in here, in the other case solvent is coming from the bottom, okay. If the solvent is light, generally then the heavy relatively solvent will come from the bottom. If the feed is heavier than the solvent, then the feed comes from the bottom actually, okay. So, if the solvent is very light, it can rise up, if the solvent is very heavy, it can come down. So, this is called a continuous column extractor. As you can see, the floor space it occupies is less. So, you have a large number of designs available. This is a static bubble column, you can see there is no agitation here, it is a bubble column. So, the solvent is entering in the form of bubbles and we have the heavies coming down or vice versa also is possible. Then we have the sieve plate, you have lots of plates with holes, so that there is agitation because of small mixing that is taking place. So, we have in a counter current fashion, you have the solvent moving in one direction and the heavies moving in another direction or the feed moving in another direction. Then the third type is agitated column. So, in these two it is not agitated, whereas you can also have a very long stirrer shaft, okay, and slowly agitate, so that you bring in certain intimate contact and enhance the mass transfer coefficient. You can have many blades here along across or along the shaft. Okay. The fourth design is spray type. So, you are spraying one of the liquids from the top and the other liquid is totally filled up. So, you are bringing in lot of new mass transfer area. The next design is called a packed column. So, you have packing here and the solvent is flowing in one direction and the feed is flowing in another direction. The fourth another type is called the rotating disc. Okay. So, you have one phase coming here, there is a large disc inside is rotating and the solvent is introduced inside the shaft. Because of the centrifugal force, it hits and gets mixed up with the other phase. So, the mass transfer rates are very high, because one of the phases is thrown outside because of the centrifugal force, that gives you a very large velocity and it gives you a very large mass transfer coefficient also. So, with this type of rotating disc we can achieve very large mass transfer coefficient with very small setup. Again more designs. This is a continuous extractor, this is called a Cooney column. Okay. So, you have sieve plates as well as agitation here. Then you have Schiebel column, you have small compartments like and then we have agitator. So, each compartment is like a stage. And then the next one is Carr column, here the agitator moves up and down, unlike this where it rotates, whereas here it moves up and down. So, all these designs are meant to bring in some intimate contact. So, as we can see, we saw two types of designs, one is mechanical agitation to improve the mass transfer and surface renewal, and the other one is the non-mechanical agitation where there are no mechanical agitation, but the contact happens because of sieve plates or because of compartments or because of formation of bubbles and so on actually. So, two designs, and you also have centrifugal devices, I showed you one picture of that. And then we have of course, in the column we have static column where you are not agitating anything, but you have, and then on the contrary you can have a column as well as with the agitation. So, 4 types totally in total, each one has got their own advantages, disadvantages, and you select based on your requirements. Okay. So, for example, stages it has, we can have a large number of stages in agitated column, you can have medium number of stages in static, and mixer settler very low. Flow rate, we can achieve very high flow rate in mixer settler, low flow rate in centrifugal. residence time generally is very high because we have to give sufficient time for it to settle, whereas in agitated columns we can have medium residence time, and centrifugal residence time is very low. Floor space occupied, mixer settler occupies very large floor space, whereas agitated or columns occupy very low floor space. So, you see some of them have advantages in stages, some of them have disadvantages in floor occupied, some of them have advantages in residence time, some of them have advantages in flow throughput. So, depending upon the physicochemical properties of the solvent you use, the physicochemical properties of the broth, fermentation broth, and what you want to extract, you select whatever you want to do actually. Okay, so, extraction of weak acids, it depends on the operating pH and their pKa value. So, you all know pKa, what is pKa? pKa is the pH at which this dissociates, right. Okay, so, you have acid RCOOH, it can dissociate to form RCOO minus plus H plus. Okay. Now, if you look at the partition coefficient K, so we have RCOOH liquid by RCOOH and then RCOOH minus. So, you have, because we have RCOOH in the liquid form, and when it goes to the heavy it will have RCOOH and RCO minus. The intrinsic partition coefficient will be RCOH in the solvent phase divided by the RCOH in the heavy phase. Now, when you look at the partition coefficient, in reality you have two terms here, because the RCOH can go into RCOH minus as well in the aqueous media, because it dissociates. Okay. So, we have two terms here. So, we have two types of partition coefficients, right. K, that is the Ki intrinsic partition coefficient, and K the real partition coefficient, and here we also have Ka, that is the association constant of the weak acid. Okay. That is ratio of RCOO minus multiplied by H plus divided by RCOH in the H in the heavy phase, and pKa is nothing but logarithm to the base 10 of Ka, that is the association constant. So, we can get a relationship between K, Ki and Ka, right. So, logarithm of 10 Ki by Ka, that is intrinsic partition coefficient by the definite actual partition coefficient, is equal to pH minus pKa. So, depending upon the pH, the Ki can change. Okay, depending upon the pH, the K can change, because your dissociation can change. That is the extraction of weak acid. So, similarly we can have weak bases also. Here we have ROH going to R plus and OH, and this depends upon the pKb. So, analogous to the weak acids, we can have log 10 Ki by K minus 1 is equal to pKb minus pH. So, in the previous case we have log 10 K minus K minus 1 is equal to pH minus pKi. Here we have pKb minus pH. Okay. So, these are the differences. Okay. So, here pKb minus pH, then here pH minus pKa. Okay. Now, let us look at a simple problem. A sugar is extracted from water with an organic solvent. It has a K value of 0.0064 and 0.0022 mole per cc at these two pH. What is the K value at a pH of 7? Okay. So, what do we have to do? We have to take log 10 K minus K minus 1 pH minus pKa. So, at pH is equal to 4, okay. I know the K value, at pH is equal to 5.8, I know the P value. So, I need to know what is the K at pH is equal to 7. So, using these two data, I can calculate both the Ka and I can calculate Ki, okay. And then I use them, and for a pH of 7 I will find out what will be the K value, okay. You understand. So, from this equation you have this equation, I know at a pH of 4 the K value is something, and at a pH of 5.8 the K value is something. So, I get two equations, I solve them, I calculate the pK or Ka, then I calculate Ki. So, what is Ki? Ki is the intrinsic partition coefficient, that is if there is no dissociation you will have you know the concentration in the liquid phase divided by concentration in the heavy phase, right. But because the base dissociates in the aqueous media, you are having extra species which is RCOO minus, that is why you get this K actually, whereas the intrinsic partition coefficient assumes there is no dissociation. So, we have the concentration of the solute in the liquid, concentration of the solute in the heavy phase. Okay. So, we can do that and thereby we can get the answer for K. So, you can see the K varies as a function of pH, Ki will be the constant. What is Ki? Once more, Ki is the intrinsic partition coefficient. So, it does not change because it does not assume if there is dissociation, but K assumes dissociation and you have an extra term here, that is why K changes as a function of pH, whereas Ki does not change as a function of pH. Okay. So, similar thing if you have problems related to bases we can do the same thing actually, right. So, of course, again here also we will have K not changing with pH, whereas K will change with pH, because as pH changes the dissociation of the weak base also follows this particular relationship. Okay, that is what this problem is all about actually. Okay, now cost plays a very important role ultimately, because I keep on talking about cost. So, at a fixed solvent to feed ratio, the amount of solute extracted increase with the increase in number of trays. If I have more trays or if I have more stages, then obviously cost will go up. So, I need to balance how much I want to extract versus cost of an equipment. So, if I am going to extract 90%, cost of equipment will be something, but if I want to go to 99%, obviously cost will go up because I may have to go for more stages. So, is it worth extracting all the 99%? So, you need to consider that. If it is a bulk chemical, maybe it might not be very useful, but if it is a very high value chemical, maybe it is useful. So, you need to balance that, right. For a fixed extraction efficiency, the number of stages required decreases as the solvent amount increases. So, if I use more solvent for the same efficiency, I will require less number of stages, correct, but then I am using more solvent, that means my equipment size has to go up because I am using more solvent. But then again if I am using more solvent, I need to get the solvent back. Okay. So, that means I need to have a distillation column to remove the solvent. So, my operating cost goes up. Okay. So, if I am using more solvent, my efficiency increases, my stages decrease. So, I am saving on cost, but my size of equipment increases because I am going to use more solvent. So, their cost is increasing. My running cost increases because I have to recover the solvent using a distillation column, maybe bigger distillation column. So, you see in some the number of stages decreases, but the size of stage increases, my operating cost increases because I need to remove more solvent. So, there is a lot of pluses and minuses and you need to balance depending upon cost, you need to balance depending upon the price of the product, is it worth it and so on actually. So, there are some relationship available, ballpark relationship, and you can look at this book Conceptual Design of Chemical Processes, McGraw-Hill. So, capital cost of a column they have said M&S, that is Marshall and Swift equipment cost index, diameter of the column, height of the column and some cost factor. So, they will take a year, for example 1926 as 100, then the year 2001 becomes 1093, year 2006 becomes 1353. So, depending upon the year we put in some number and then F is the cost factor. This cost factor depends upon the pressure cost effect, material cost effect. Suppose if I am using very exotic material, cost goes up. If I am using mild steel, it is cheaper. If I am using atmospheric pressure, it is cheaper. If I am going to 10 bar pressure, then cost goes up. So, this cost factor takes care of these two terms, and M&S starts from the year 1926 as 100 and then keeps multiplying. As you can see, for year 2006 it is 1353. So, cost of vessel in 2001 is 15,000. What is the cost in 2006? So, I can put it those numbers 15,000 and then I will put in the M&S factor and so on, I will get it is about $18,565. Size, again if you remember I talked about the 0.6 exponent type of 0.6 where cost of B is equal to cost of A, size of B by size of A raised to the power n. So, these numbers can change between 0.3 to 1.72. So, if I know the cost of a 2000 gallon vessel is $15,000, what is the cost of a 5000 gallon vessel, I can put in, and I put in the proper n. Here I have taken as 0.88. There are data available, for example, for different equipments we can see the n value is given here for different equipments, for agitators, for collectors, for conveyors, centrifuges, evaporators, tanks, heat exchangers, pumps, you can see for different equipments the n is there. So, we can use this n. So, I know the cost of the equipment, I can find out cost of a new equipment using this this rule actually. So, but then if you have a column, you are also going to have internals, right. So, you need to have one more term for the internals. Internals means packing, different types of packing material may be there. So, you need to add that cost also into the cost. So, the total capital cost will be capital cost of the column, capital cost of the internals. Okay. So, annualized capital cost will be divided by n, n is the age of the equipment. So, this gives you some idea about the depreciation. Now, operating cost will be electricity, labor, all those things will come into operating cost, right. Okay. So, maintenance will be certain percentage of capital cost. So, the total annualized cost is all these terms added up together. Okay. If you take mixer and settler type of extractor, we have some relationship for capital cost. Okay. So, it is 14.8 10 power 3, whatever capacity you want, put in the M and S factor, and then this is the reference capacity, okay, and you are raising it by 0.7. Here the exponent is 0.7, okay, that is for the mixer settler type. Similarly, for a continuous centrifugal extractor, we have some formula here, and here the exponent is 0.58. Okay. This is using a material of 316 stainless steel as a material. Okay. So, you see that different types of equipment we can have different cost, and depending upon the material of construction the cost will change. All these cost it just gives you an idea when you are selecting equipments. Cost should play a very important role, but if you want to know the exact cost you may have to go to the vendor and find out what is the exact cost, but it gives you an idea about should I go for a centrifugal extractor or mixer settler or a column extractor and so on actually. Okay. Thank you very much.